So the last thing we've got to do is we're not going to do any more reaction mechanism. It's the same reaction, but what we're going to look at is what happens once you get a substituted ring. So we've been talking about these reactions with just benzene, but what happens if something else is already on that benzene ring? Okay, and what we know is that there are, what we know is that there are already, that the different substituents will have different effects. And what we're going to do is we're going to classify the different substituents, and the main effect they have is whether they are electron withdrawing or electron donating. And we'll understand what that means in a minute. So an electron withdrawing group is one like we looked at, for example, the nitro group. Something which draws electron density out of the ring. And that will have two effects. One is it will make the ring less reactive to start with, okay, because the reactivity of the aromatic ring is driven by the electron density in the ring. If you've taken electron density out of the ring is has less electrons, so it is less nucleophilic. It doesn't react as much. And the other thing is, if the electron withdrawing group is on the carbon that has a carbocation, what we know is the carbocation is more stable if we push electron density towards it, because a carbocation, a positive charge is saying this is an area which lacks electron density. So if we can push electrons towards that, it will stabilize it. So of course, if you have something which is electron withdrawing attached to it, it's going to make that carbocation, that positive charge, even more positively charged, and that will make it more unstable. So conversely, if you have an electron donating group, it's going to do the opposite. It's going to push electrons into the aromatic ring. It's going to make it more nucleophilic. It's going to have more electrons that it can use to react with an electrophile. And equally, if the positive charge ends up sitting on the carbon that the electron donating group is attached to, it will help to stabilize that carbocation. And what we'll see is that they are the key to it. Can we stabilize or destabilize that carbocation? Because that will influence where the molecule reacts. Last time we had a brief look at, if you had a substituent, we had this idea of ortho, meta, and para. Yeah, so ortho was the carbon next to the substituent, meta was the carbon 2 away, and para would be the one opposite. And we're going to look at that in more detail. So, the ortho and the para positions are predominantly electron deficient. Okay, what we mean by that is, let's have a little look. Okay, so if we draw our ring, okay, and we have an electrophile attached to it, we have a positive charge there. Okay, so that's what happens in the reaction. That's the reaction mixture we've been doing all along. I'm just not drawing the first bit. I'm showing you the product, the carbocation product. So we have this positive charge. Now, the electrophile is our substituent. So at the moment, this is the ortho position to that electrophile. It's the one next to it. Okay, if we draw the resonance structure where we say, well, let's take the electron density from here and use it to move that, stabilize that carbocation, move it around, the charge will end up over here. Okay, our electrophile is still here. We've got our hydrogen. Okay, so we can see now we've moved that charge around. Now it's skipped over the meta position, so the meta position would be this one, skipped over that one, and it's on the para position. So this is why we're saying that if you have a substituent there, as part of this reaction mechanism, okay, the ortho and the para position within the mechanism are electron deficient. When we add the electrophile, the ortho and the para position are the ones that end up with the positive charge. And again, we can move it around for that final resonance structure. And it ends back on an ortho position again. Okay? And that's the other key thing to remember. There are 2 ortho positions, there are 2 meta positions, and there's only 1 para position. So what that tells us is we've just in the slide before said if the substituent is on the carbon which has the positive charge, if it's electron withdrawing it will take electron density away, if it's electron donating it will push electron density in, so it's going to either destabilize or stabilize the carbocation. So therefore, if we've already got a substituted ring, the ortho and the para position are going to be affected more than the meta. And again, electron donation will stabilize, electron withdrawal will destabilize. So if we have some other substituent here, X, Y, okay, those ones will have more of an impact on this reaction than if they were in the meta position. So what we'll do is we're just going to unpick that a little bit more. We're going to have a look at a couple of examples to see if we can understand what's going on. Okay, so we're going to start by talking about what's called the inductive effect. And we're going to look at inductive and resonance. So there are 2 different effects, and there are 2 different ways of stabilizing that carbocation or destabilizing the carbocation. The inductive effect is what we've talked about with stabilization of carbocations, the difference between a primary, a secondary, and tertiary. The idea that if you have electron density that can be pushed through a sigma bond, that's a kind of inductive effect. So anything that pushes electron density from a sigma bond will give you this inductive effect. Resonance is when we can use things like lone pairs, we can use pi electrons. Okay? So the inductive effect arises from the substituent's ability to donate electron density or remove it through sigma bonds. So let's have a look at what would that look like in the ortho example. So we're going to start, this time we're not just going to draw a standard benzene, we're starting with a substituted benzene. We've got a CH3 group on it. I'm going to draw it CH3 for this one. Afterwards I'm going to just draw it as a line, but just to remind you, it's a CH3. So what's going to happen now if we have that CH3 reacting with an electrophile? Okay. Well, we're looking at the ortho position, so the one we're looking at is this one here. So that's the one that we're going to do our reaction on. So we're going to use the electrons from between these 2 carbon atoms to do our reaction. Okay. We've got our CH3 there. We've got our E. And we've got our positive charge. Okay. So at the moment we think, well, there is nothing helping that electrophile, is there? That positive charge, that carbocation, there's nothing attached to it. But what about if we draw the resonance structures in? Okay, so we remove that charge around the ring. Okay, we are over here. And then again, if we take the electrons from here, what we can see is that we can end up with our positive charge on the carbon that has the methyl group attached, that has the CH3. And we can almost see it just from the information we know about primary, secondary and tertiary carbocations. In this example, the first 2 resonance structures, that would be considered a secondary carbocation. It's got 2 carbons and 1 hydrogen. But when we get to this final one, okay, it's a tertiary carbocation. It's got 3 carbons next to it. And we know that that is more stable than the secondary one. So by having that methyl group, which effectively can push electron density through, so it can push electrons down through this bond into that carbocation, it can stabilize it. Now, that's a favorable example. Let's think what would happen if we had a nitro group there instead. So if we draw the nitro example, Okay, so all I've done there is I've replaced that methyl group for a nitro group. Again, hopefully we start to look at that and say, well, we have got two positive charges on atoms next to one another. Do we think that's going to be a favourable situation? We know from things we've done before, it's the example, if you take two magnets, you try and put the two positive poles together or the two negative poles together, they repel one another, don't they? Same thing here, you've got two areas that lack electrons right next to one another. They are going to be so unhappy, and that's going to be such an unfavourable example that isn't going to work. Okay, that reaction to start with wouldn't happen because that nitro group is really disrupting the stability, the stabilisation of that carbocation. It can still move across two bonds, but when it gets to this situation, it's right next to that nitro group, that's very, very unfavourable. So we can see that an electron donating group is going to help stabilise this situation, but an electron withdrawing group is going to be detrimental, it's going to destabilise this. So electron donating would be favourable for the reaction to occur, electron withdrawing would be unfavourable for the reaction to occur. We'll have a very quick look at what happens with the power example, so we can do the same thing if you think we have our CH3 up here, and we have our electrophile down here, so we do exactly the same reaction, okay? We've added our electrophile, it's now in the power position to the methyl group. Yeah, it's directly opposite. We can draw the resonance structure. This time we only actually have to draw one to get to where we want to be. The electrophile's down here, the methyl group's up here. And the methyl group, that carbon is now going to have the positive charge. So everything I've just said about the ortho example, about the donating groups being able to push in and stabilise that carbocation, the electron withdrawing groups withdrawing the electron density away from it, or we're having two positive charges right next to one another. The same thing applies here. So with the power position, we get the same thing occurring. So we've done the ortho, we've done the power. It seems sensible. Let's look at what happens with the meta position. So we're going to do the same thing here. We have our CH3. We have our electrophile. We're going to do exactly the same reaction. Okay, we've added our carbocation, so that's the start of it. And then we draw our resonance structures. So we move the electron density around. And the first one we do doesn't land on that methyl group, does it? It doesn't land on the carbon that's attached to the methyl group. If we move it around again, sits at the bottom, okay? So with the meta position, the substituent doesn't impact on the carbocation at all, okay? Because the carbocation in our resonance structures never lands, it never sits on that carbon there. So the substituent can't really do anything. The only thing it can do is generally withdraw or donate electrons into the ring to start with, but that's just going to be whether the ring itself is reactive or not. So the most important thing though is, with an electron donating group, with the ortho and power, we can see there's some advantage to it, can't we? If we've got a substituent in the ortho or the power position, it stabilises, it gives some driving force, some stability to the reaction as a whole. But with the meta one, there is no change. There is no influence of that substituent. So that means electron donating is good for the ortho and the power, but we know that electron withdrawing groups are detrimental to the ortho and para. So what we're going to discover is, if you have a substituent and it's electron donating, it's going to favour substitution of the ortho or the para position. If we have a substituent which is electron withdrawing, it is going to favour substitution of the meta position because it doesn't have an impact. It doesn't affect the positions at all. It doesn't stabilise or destabilise that carbocation. So that's the inductive effect. We also just have to take into account that we also have the resonance effect. The principle is going to be the same at the end of it, this idea of ortho and para stabilising, being positive if you have an electron donating group and negative if you have an electron withdrawing group. It's just a slightly different way of stabilisation. So let's have a look. So this resonance is being able to use a lone pair to do something. So the example that we will use to start with is to take something like a nitro, an amine group. Okay, so NH2. Okay, so if you add an NH2 group to the ortho position, so if you've got an NH2 group, you're going to do your reaction and add your electrophile to the ortho position, it will look like this. We know we can draw those resonance structures. We've drawn them before, so we're just going to skip straight to the one that's important. And that is when we end up here. Okay, so that's the one that's important, where there's one in between that I've missed out just for the time. So we could look at that and we can say, well, can it do an inductive effect? Can it donate electron density through the sigma bond? And actually it won't. So there's a bit of a conflict here because nitrogen is more electron negative than carbon. So in that sigma bond, the nitrogen will do the complete opposite to what we want. It's going to withdraw the electrons in the sigma bond towards itself, which will destabilise the carbocation. However, it has a handy lone pair of electrons. So that lone pair of electrons can form an extra resonance structure in which the cation ends up on the nitrogen. So this is a way of stabilising that carbocation through yet another atom, so another resonance structure. So the NH2 group, although inductively it would withdraw, resonance, it can donate that pair of electrons. So we'll cover right towards the end the difference between those and which one we think is better or worse, but we just need to be aware some are inductive, some are resonance. So that would be the situation for the ortho, so that's exactly the same as we did for the inductive effect. It's just this very last bit. Instead of just being a pushing of electrons down the sigma bond, we're actually using a lone pair of electrons to help stabilise that charge. The para would look very similar to that, but let's have a look at the meta because that's the other one that's important. So we have our electrophile, we do exactly the same starting bit. We end up with our electrophile in the meta position, and once again we just need to show through one resonance structure. Let me draw that better, I'm rushing it. But again, exactly the same thing, we do not have that positive charge sitting next to the substituent that has some effect, okay, whether that's electron withdrawing or electron donating. So substituents in the meta position really don't have an impact on whether it's stabilised or destabilised. So those two things, I've shown you a couple of different things. Just have a look back through them. Try to make sure that you understand why, if you've got a substituent, if the carbocation can land in the resonance structures on the carbon that has the substituent already attached, there will be an effect. Electron donating will be positive, electron withdrawing will be negative. Okay, one will be stabilizing, one will be destabilizing. And then just rationalize with yourself, if it adds in the ortho, meta or para position, do you see a positive or negative effect, or is there a net zero because the substituent doesn't get involved? I'm going to skip the para just because it's exactly the same as it was before, and just because Rav took up a little bit of time. So the last couple of things is to look at one, activation of the aromatic ring. Okay, so this is about, although I've said that the electron donating group or the electron withdrawing group doesn't impact on the substituent, or it doesn't destabilize or stabilize the carbocation, what it does do is change the reactivity of the ring to start with. So, electron donating groups. So let's have a look at an example. Okay. If you have an electron donating group, so O-methyl is an example of one. Okay. The lone pair of electrons can push themselves into the ring. Okay, so you can, if you form a double bond here, the carbon has got too many, so we break one of the other double bonds, which is here, and we can draw a resonance structure. And we can put a negative charge on that ortho position. We can then draw another resonance structure. In which the negative charge sits on the para position. So this just helps us to explain again that the ortho and the para position, if you have an electron donating group, they are going to be more reactive. So not only do we have this, if we add our electrophile to the ortho or the para position, we get this additional stabilization of the carbocation with an electron donating group. We also have that those two positions to start with are more reactive anyway. And this hopefully answers a little bit of the question some people have asked, can I draw my aromatic rings with circles in them, which is how we know, how you might have been trained to do it. But it's very difficult to show how that movement of electrons explains why the ortho and the para position are more reactive. If you've just, if you've got your substituent here, it's very difficult to show that those two positions gain a little bit of electron density. So what we're saying is those have more electron density, therefore they are more reactive. Okay, and you can see, I'm hoping, the converse effect will happen as well. If it's an electron withdrawing group, what's going to happen to those two positions? If you're pushing electron density into them this way, an electron withdrawing substituent is going to draw electrons away from them. So you can deactivate the ring with an electron withdrawing group. So very quickly, you'd start with your aromatic ring with your nitro group. So if I ask you about an electron withdrawing group, draw me a nitro group. It's the most classic example and the easiest one to understand. So think about if the nitro group is withdrawing electrons away, it's going to do this. And you can already see that that means that ortho position has, a positive charge in this resonance structure, therefore it's going to have less electrons there, which means if it's reacting with an electrophile, it's not going to because it doesn't have the electrons to do it. And we can then draw the other resonance structure where we put that positive charge at the bottom. Okay, so the ortho and the para position again have this destabilizing effect there. So the most important thing to recognize is that in this instance, the meta position again, no effect. The ring itself is less reactive because it's had electrons drawn away from it, but that meta position, out of the three, is the one that actually is the most reactive with an electron withdrawing group because it doesn't have this positive charge on it. So you can think of this as, if you have an electron withdrawing group, that the ortho position and the para position are all slightly delta positive. And if we're talking about this acting as a nucleophile needs electron density. So if it's delta positive, it doesn't have as much electrons as somewhere else. So it means that they are not going to be as reactive, those 2 or 3 positions when you have an electron withdrawing group attached. But when you have the electron donating group, we can do exactly the same thing, and we can recognize that this now is delta minus. So it has more electron density in those 3 positions than the others. So therefore, if it's acting as a nucleophile, the more electron density, the better. So therefore, that is going to be more reactive. So what you'll see is we'll ask you things like, okay, here's a substituted aromatic ring. Here's some conditions, which are the ones we've seen, you know, Cl2 and AlCl3. What's going to be the product? And we're wanting you to go, okay, that's electron withdrawing or that's electron donating, which means that the next reaction is going to put it either in the ortho, the meta, or the para position. And just the last thing is that some functional groups, and we saw the amine, can do both. It has this inductive and it has this resonance contribution. And the intensity of those is what we need to consider. So, if you think about the amine example, okay, so we have our NH2, we have our ortho position here. We have 2 things we can do. One is this will draw electrons away from that positive charge. Okay, so that is going to be a bad thing. That's going to be destabilizing. If we use the lone pair of electrons, that's going to give us a resonance structure. Okay, and that's going to be a good thing. That's a really bad tick, isn't it? Let's try that again. Okay, that's going to be a good thing. So this functional group can do 2 things. It can do an inductive effect, which is electron withdrawing. It can do a resonance effect, which is electron donating. One of them is good, one of them is bad. How do we decide overall what does this do? Well, think about it. The inductive effect is kind of I'm taking away, there's a pair of electrons that we share, and in theory they should be in the middle. We should share them equally. But because I'm more electronegative than you, I'm going to pull away a little bit towards me, so you're going to lose a little bit of your share of those electrons. I'm not taking them away completely, but I'm just giving you slightly less of it. So that's the inductive effect, the bad negative effect. The resonance effect, which is the positive one, is here. You don't have enough electrons. Here, take 2 of mine. No, we'll share them. I mean, you've not had hold of these electrons before, but at this point, I'm going to give them to you. Which of those do you think is going to be the stronger effect? Which one's going to stabilise that positive charge more? It's going to be that here, have some electrons that you never had in the first place. So the resonance effect is a much stronger effect than the inductive effect. And so therefore, an amino group, although it can do both, overall globally, it's electron donating. And that will be the same whenever you look at any of these things, where there's this trade-off between you know, inductive versus resonance, positive versus negative, which one is it going to be? Now, of course, chemistry being chemistry and science being science, there's always the exception. There's always the one that doesn't follow the rules. And for us, that's the halogen. Because halogens have very strong inductive effects, haven't they? If you draw your halogen, okay, so you've got your halogen. We know that halogens are incredibly electronegative, aren't they? Yeah, incredibly electronegative. So they really are going to pull the electrons away from that positive charge. They're going to have a really large negative inductive effect. But they are not a classic electron withdrawing group. Although they do it inductively, they have a very weak but possible resonance effect. Again, they don't really want to because halogens don't like giving up their electrons. So they really wouldn't want to do this, but they're forced to. You know, this positive charge is right next to them. If they want it to remain there and to be stable, they need to donate a bit of their electron density. So they will do it. So what that means is, I've drawn over it, they are deactivating like an electron withdrawing group. Okay, so they make the ring less reactive, but ultimately they direct ortho power because they can provide a small amount of stabilization because that resonance effect, although it doesn't want to happen, it is still stronger than the negative inductive effect. But they do reduce the overall reactivity of the ring. We are nearly there. So the last one, so we've talked about, I showed you that resonance has a positive effect there, but it can have a negative connotation. So if you take groups that can do more resonance, then it becomes a problem. So if we look at this, okay, so we've attached a carboxylic group, so we've attached it through the oxygen, okay? This has the effect of being able to stabilize. Yep, so if you stabilize that, you would end up with this kind of you would end up with a resonance stabilization. But the other thing it could do is use its lone pair, and instead of going this way, it doesn't do that. It takes it this way. And you end up with two positive charges next to one another again. So there are these conflicting things. Again, it can support, it can take away. You don't have to remember all of them, you just have to remember that they occur. And then what we can do is, the next slide is the most important one. Okay, you've got these things. We have a nice little table that tells you these are the common groups that you're going to come across. Okay, I've explained to you the reasons why there would be electron releasing or electron donating and electron withdrawing, but ultimately knowing this is going to help you. So what we can see is that there are some electron donating, or they've called them electron releasing groups, which we know are ortho and para directors, things like amines, things like hydroxyl groups. There are some which we've just looked at that are moderately electron releasing, okay? They're not particularly strong because they have that conflicting resonance going on. And then you've got the electron withdrawing groups. And the electron withdrawing groups donate to the meta position, or direct to the meta position. And again, you've got some strong and you've got some moderate ones. So what you really need to do is go and look at that slide and make sure that you start to understand why. Why are those groups what they are? If you're not sure, go back through these lecture notes, go and have a look in the textbook, because that will also give you the explanation of why. And it's going to come down to, can they do an inductive effect? Can they do a resonance effect? Is that inductive effect positive or negative? And of course, the exceptions are, you have these withdrawers, which destabilize but are ortho and para directors. So we've got 2 slides that we just need to finish and then we're done, okay? So I will just finish those, otherwise, we're going to have to do this tomorrow. So I'm going to skip the test. You can do that at some other time, okay? The only thing I want to now, just to make you appreciate, okay, is that when you have these substituted aromatics, you need to think about, when you're doing your synthesis, if you want to add 2 groups to an aromatic ring, think about the order in which you would do them. So, for example, here, if you did the acylation first, you added the acyl group, okay, then you get something which is moderately deactivating, okay? Then you can add the nitro group and you end up with this M-nitroacetophenone. If you didn't know about the effect of substituents, you might think, well, we'd do the nitro group first and then we would try to do the acyl group. But the nitro group, this, we've just found out is deactivating. So if you add the nitro group first, the following reaction just wouldn't work. Okay, because the product, that nitro product, isn't reactive enough. So we're thinking we can create the same structure by doing 2 different reaction mechanisms, but in actual fact, you would do it this way rather than the one at the bottom. So that's just one thing to remember. Again, I'm not going to go into detail about it. It's just to have an appreciation that you might need to consider the order in which you do things. And the final one is, if you've got, what we've learned is that electron donating groups can direct ortho and para. So that would suggest that you might end up with multiple things. You'll end up with an ortho substituted one and a para substituted one. So, but again, if we think about what we're doing with larger groups such as this, the ortho position isn't as available. You've got this kind of steric block here. This makes it very difficult for the electrophile. So the electrophile's out here. It can't move in there because that larger group is there. So in that case, you end up with predominantly the para product with a minor bit of the ortho. We sometimes get a bit of meta. It just, that's the case. But if you do it the other way round, okay, if you have the same kind of thing, that you've got a small substituent here, but you have a large electrophile, the same thing will happen. The large electrophile can't get to the ortho position, so it will predominantly, again, go to the para position. So if you're being asked, look at this structure, predict what you think the product will be, and it's electron donating, and it will direct to the ortho and the para position, what you have to ask yourself is there anything that's stopping it from getting to the ortho position? Because if there is, then it's more likely that you would end up with a para product rather than the ortho product. Okay? That is just, the added extra. I mean, the stuff to understand really is all the reaction mechanisms and the directing effects. And this is the kind of, if you can get your head around it, it's useful to know. So what you need to be able to do from this bit of it is you need to be able to explain the directing effect of those withdrawing and donating groups. Why is it that a withdrawing group directs to the meta? And that's because it doesn't influence the carbocation stability. And what is it about the ortho and para that means electron donation favours those positions? And again, it's because you can stabilise that carbocation. So those are the things you need to take away from here. And you need to be able to explain why something is electron withdrawing and why something is electron donating. I'm sorry we've gone over time. That's because obviously Rav came and talked to you about something really important. If you would like to ask me the question, feel free to ask me now. Does anyone want to ask me if I'm going to be here next week? I will be here next week, so you will have the lectures.